And then we explored how logistic regression solves this problem by applying the sigmoid function, ensuring outputs always remains between 0 and 1. And we also introduced the log odds transformation, and which allows logistic regression to model probability in a linear form. And finally, we implemented logistic regression and saw how it provides a clear decision boundary, making it the ideal choice for classification task. Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, we are going back to our machine learning series. And today's session, we are going to explore one of the most important classification algorithm, logistic regression. Dear friends, before diving on to logistic regression, let me just have the recap of machine learning. Yes, dear friends, machine learning algorithm techniques can be broadly classified into three categories. Yes, it is supervised, unsupervised, and reinforcement. In supervised techniques, of course, algorithm in supervised or trained using labeled dataset, where the algorithm learn from each category of input. And of course, it is simply specified as like a task driven. And when coming towards unsupervised, yes, it is all about data driven, and mainly it has subdivided into clustering. And when going on towards reinforcement, of course, it is simply specified as like learning from rewards or mistakes. Okay, so back to the supervised. Yes, dear friends, it is furthermore classified into classification and regression. So regression procedures are applied when there is a relationship between the input variable and the output variable. So this technique is commonly used to forecast continuous variables such as weather patterns or market trends and other phenomena. And when coming towards classification, of course, when the output variable is categorical, such as yes or no, or 1 and 0, male, female, true or false. So these comes as like classification methods, and these methods aim to classify input data into predefined categories or classes. Okay, dear friends, a logistic regression is a statistical model used to analyze and predict binary outcomes. It's commonly used in finance, marketing, healthcare, and social science to model and predict binary outcome. And dear friends, logistic regression model uses a logistic function to model the probability of a binary response variable. So given one or more predictor variable. And this logistic regression is considered as a regression model also. So this model creates a regression model to predict the likelihood that a given data entry belongs to the categorical label 1. A logistic regression model, the data using the sigmoid function, much as linear regression, assumes that the data follows a linear distribution. But here we would have a small confusion. Why can't we use linear regression instead of logistic regression? Yes. Before answering to this question, let me just give a small explain about what is a linear regression concept. Then only we can just understand it better when we just go on towards logistic. Dear friends, using linear regression for categories. See, of course, here I have already specified linear regression. It is used in continuous data. And towards logistic regression, it is for categorical. Okay, now I just take this towards this linear regression. Using linear regression for categories is like trying to fit something as like square peg into a round hole. It might work, but it won't give us accurate results like logistic regression does. Let me just give you a small mathematical explanation of what is linear regression. Of course, we already have discussed that is linear regression. It has an mathematical function. Okay, mathematically it is specified as y is equal to mx plus c, and here y it is the predicted value, and of course m it is the slope of the line, and x of course it is the input data, and of course you can just specify c as an intercept. Okay, so we can forecast this y value such as using these values. And how this would be observed is, yes, kindly just observe this exact diagram. The x values here, it is represented by these blue dots. Okay, that is the input data, and we can now compute slope and y coordinate using the input data to ensure that our projected, that is this red line, okay, covers most of the location. We can now forecast any y value of anything as like a given text, this one or this one or this one, okay, by using this line. One thing to keep in mind about linear regression is that it only works with continuous data. If we want to include linear regression in our classification model, we will have to adjust one algorithm a little more. First, we must choose a threshold, so that if our projected value is less than the threshold, it belongs to class 1. Otherwise, it is class 2. Okay. Now, if we are thinking, that's a simple job, just to create, and this is as like our linear regression with just as like a threshold. Is it simple? No, actually we must specify the threshold value manually and calculate the threshold for huge data set. That would be very impossible. So furthermore, even if our anticipated value vary, the threshold value will remain the same. Okay, so now let we assume we have information about this. This actually it is all about a tumor. Okay, so we just know about tumor size and malignancy. Okay, so because this is a classification issue, we can see that all the values will fall between this 0 and 1. Okay, so every values that is within 0, 1. And by fitting this best fit regression line and assuming a threshold of 0.5. Okay, so we can do a very good job with this line. This is the regression, and we can select a point on this x-axis, and of course on this x-axis where all the values to the you can just say is this is the baseline. Okay, whichever it is in left side of this line, yeah, it consider as negative, and all the value which is right or regarded as an positive. But what if contains an outlier? Here you can just also specify when we just take on towards this threshold. Of course, we can easily evaluate this negative and positive. But when we just have here, let me just have an outliers here. But things would become smattable. That is for this 0.5. If I just have like this, kindly just observe. I'm just having this threshold line. Okay, and I'm just making here, and what about this 0.5, and how about this 2 points and towards this 2 points, and this exact 2 points has a confusion whether I have to make it as a negative or it is a positive. So this is a big confusion when you include something as like an outlier. And even if it fit the best form regression line, we won't be able to determine any point where we can distinguish classes. It will insert some instance from the positive class into the negative class. And here the green dotted line, of course, which I have just previously specified, separates the malignant and benign tumor. However, it should have been a yellow line that clearly separates this exact point. Okay, that separates the positive and the negative. And as a result, even the single outlier can just throw the linear regression estimation off. And it's here the logistic regression come into play. How? Of course, kindly just observe, dear friends. Here what I'm just going to do is, let me just have this. Of course, this is what we have. Okay, and this is the 0 and 1. Whatever be the data points here below the 0, yes, it is considered as 0. And even if it is an outlier, and whatever the point this is above 1, of course it is considered as 1 only. So now what we are just going to have, of course we have a best fit regression line, and kindly just see whatever be this outlier, we are just going to trim here. And whatever be the outliers that is below 0, yes, it is considered as below 0. And now I'm just going to trim whatever be the points here and towards this point here, and when on just making this is what our sigmoid. And of course, let me just take this in solving towards the function. Kindly just observe, dear friends. So solving from this, how it is possible? It is by using logit function, and logit function to the sigmoid function, which is like turning raw data into something we can actually use. So sort of like turning a block of wood into a finely crafted sculpture, as like that. So here logistic regression can be expressed as log of p of x divided by 1 minus p of x, which is equal to beta 0 plus beta 1x. And here kindly just observe, dear friends, this p of x divided by 1 minus p of x, it is termed as like odds. And whatever be this in the left hand side is called as logit function or log odds function. Okay. And the odds or the ratio of the chance of success to the chance of failure. And as a result, in logistic regression, a linear combination of input is translated to log of odds with an input of or with an output of 1. And yes, the inverse of the aforementioned function here, it would be as like p of x, which is equal to e to the power of beta 0 plus beta 1x divided by 1 plus e to the power of beta 0 plus beta 1x. Dear friends, the mathematical sigmoid function that can be specified as like f of x, which is equal to 1 by 1 plus e to the power of minus x. And here towards the sigmoid function, kindly just observe, this is the exact sigmoid function which produces as like an S-shaped curve. So it always returns a probability value between 0 and 1. So the sigmoid function is used to convert expected value to probability. So the function converts any real number into a number between 0 and 1. So we utilize this sigmoid, okay, to translate the prediction to probabilities in machine learning. And kindly observe, dear friends, logistic regression is one of the simplest and most widely used algorithm for classification, particularly binary classification. While it shares some foundational similarities with the linear regression, it modifies the approach to ensure that the output represents probability rather than continuous value. And of course, I just want to specify one thing. See, when we just start with a linear model, of course, in linear regression, we model the relationship between the input future x and the target y using a linear equation. What is it? So y is equal to dou t x plus b. And here this dou represents the weight, or you can also specify the coefficient of the feature, and the b, it is the bias, the term. Okay, this model works well for regression problem, but in classification, we need our output to be constrained between 0 and 1, representing the probability of belonging to a particular class. So for that, what we are just doing, we are applying the sigmoid function. And since the linear model can output any real number, of course, any real number from negative infinity to positive infinity, we need a transformation that maps these value into a valid probability range in classification as like 0 to 1. So this is achieved by this sigmoid function. Of course, previously we have just seen what is the sigmoid function, 1 by 1 plus e to the power of minus x. And by applying this to our linear model, we obtain p of y is equal to 1 by x, which is equal to 1 by 1 plus e to the power of minus dou t x plus b. Okay, and here, yes, this transformation ensures that the output is always a valid probability, making it suitable for classification. If the probability is close to 1, the model is confident that the instance belongs to class 1. If it is close to 0, yes, the model predicts the class 0. Okay, yes, dear friends, now that we covered the theoretical foundation of logistic regression, it's time to bring it to life with a practical demonstration. But before we implement it, let's first answer an important question. What happens when we try to use linear regression for classification? To explore this, yes, we take a real world data set where we predict whether a person will buy insurance based on their ages. So we will first apply linear regression and visualize its prediction. Then we will see how logistic regression naturally solves the issue of linear regression and why it is better choice for classification task. Okay, let's move on towards the code. Okay, so first of all, let me just okay, so here I just make use of the warnings. Okay, and yes, after making these, yes, of course, you all know, usually I just make use of some need and necessary import functionalities, the libraries. Yes, here I have just given NumPy, Pandas, Matplotlib for plotting. And of course, we are just going to make use of linear regression, okay, and logistic regression comparison. And of course, a small function animation I have included to have an animated functionality. Okay, so I just execute this too. Okay. Difference in, as I have already specified, so imagine we have a data set whether we want to predict whether a person will buy insurance based on their age. The outcome binary, that it would be either 1 or 0. Okay, so of course it would be simple, but kindly just observe this is what the exact age and towards the output 0s and 1. And dear friends, now let me just add few individuals as like here age is 80, 85, 90, 95 and towards 100, all of whom have bought insurance. Okay, let I just execute here. Okay, so see here, dear friends, here we notice younger person, that is these are the exact younger person are less likely to buy insurance while older persons tend to buy it. But will a linear model capture this trend as well? Let me just explore. And how this be handled when a linear regression applies. Okay, so first of all, what we are just going to do is, as I am not going in depth towards each and every line of the code, and of course I just share this code in the description, you can have a look, and it is not much more tedious or towards confusion, just to plot it. And here I have just given a function where we apply linear regression, thus this one. Okay, so here kindly just observe, this is all the things towards the plotting. Everything it is as like a plotting the data, and of course it just gives the labeling and towards the title as like linear regression. Okay, so yes, we apply a linear regression and we want to have an animate how it behaves as we introduce outliers. And here's, of course, I have to specify one thing, dear friends. Of course, the problem in linear regression extends beyond 0 and 1, even predicting impossible probabilities like -2, okay, minus 0.2 and 1.3. Okay, let I just give you the output here. And before going on towards that, yes, logistic regression also we have just included, and that is designed for classification problem. Instead of this straight line, of course, kindly just see, this is the linear regression when we just include the outliers, how it behaves. And of course, this is the dotted line where we have included the threshold. And in this logistic regression, yes, instead of the straight line, it creates an S-shaped curve, ensuring prediction always stay between 0 and 1. See the difference, dear friends. Logistic regression predicts probabilities smoothly, keeping them between 0 and 1. It also identifies a threshold age where buying insurance becomes more likely. And yes, dear friends, and that brings us towards end of this today's session. Yes, we have just I give you a small recap. And we started by understanding why linear regression is unsuitable for classification. It predicts values outside the valid probability. And then we explored how logistic regression solves this problem by applying the sigmoid function, ensuring outputs always remains between 0 and 1. And we also introduced the log odds transformation, and which allows logistic regression to model probability in a linear form. And finally, we implemented logistic regression and saw how it provides a clear decision boundary, making it the ideal choice for classification task. Okay, dear friends, we dealing with binary classification problems always prefer logistic regression over linear regression. And I hope this session helped clarify these concepts for you. If you enjoyed this video and found it useful, don't forget to like, share and subscribe for more hands-on machine learning tutorial. Stay curious, keep experimenting, and I will see you in the next video. Thank you, dear friends. Happy learning.